Okay, so welcome everyone to the ICTS String seminar. Today we are very happy to have Evita Verheijden from the University of Amsterdam, who will tell us about no-page curves for the de Sitter horizon. So please, Evita, take it away.
Thanks, Victor, and thanks for inviting me. So today I will talk about this paper we recently put out, titled "No Page Curves for the de Sitter Horizon," with Joshua Kames-King, who is a collaborator in Bonn, who's a graduate student finishing this year, and Eric Verlinden here in Amsterdam. And maybe to set the stage, let me try to explain why I think this is a topic worth studying. So basically, I guess the main motivation is that de Sitter space is, to good approximation, a toy model for our own universe. So it's basically a sphere that starts out infinitely large at the beginning of time, and then shrinks to a minimal size and increases again to maximal volume. And especially in this later phase, we recognize both inflation, but also the current expansion phase of our universe. And a very, maybe the most salient feature of de Sitter space is the fact that any observer sitting inside de Sitter space is surrounded by what's known as the cosmological horizon. Cosmological horizon has a temperature and a corresponding entropy, and it's basically the end of what we see due to the expansion of space. And if we want to understand our own universe, it's important to understand the cosmological horizon, and in particular, its entropy, which is rather mysterious. And especially for me, I guess, this is working towards the goal of building a microscopic description of our universe. And in the work that I will discuss today, what we did is we applied lessons learned from black hole holography, and in particular in the context of the black hole information problem in anti-de Sitter space, to learn about the cosmological horizon. So that's also where I will start today. I will start by very briefly reviewing some key ingredients of the recent progress in the black hole information problem. And then I will make the transition from ADS black holes to empty de Sitter space and introduce a model that we constructed, in which we start from three-dimensional de Sitter space and then do a reduction down to 2 dimensions, thereby creating a gravitating region and a thermal bath. And then we are able to compute using the three-dimensional system as an auxiliary system, the fine-grained entropy, both at future infinity and inside a static patch. So please interrupt me at any point if you have questions or if something is unclear. I'll be happy to discuss. I didn't prepare too many slides, so I think there should be plenty of time for discussion. Okay, so here's my one-slide summary of the black hole information problem. And the question at stake is basically, do black holes form and evaporate in a unitary fashion? So here's a cartoon. We throw stuff inside a black hole radiates. In principle, we have no access to the degrees of freedom behind the horizon, but one could ask, if I collect that radiation, can I retrieve the information that was inside it? And this has been a paradox for a long time, because at first sight, it seems like you wouldn't be able to retrieve that information. The black hole is just radiating with a black body spectrum. But since it's built on unitary laws, one would say, okay, no, this has to be a unitary process. This paradox has a formal resolution within holography, where we know that the dual CFT is unitary. So hence, any process within the bulk should also be unitary. A sharp formulation of this puzzle is in terms of entropy. One way to think of it is in terms of entropy of ignorance, where collecting the radiation semi-classically, or just from a gravity perspective, gives an ever-increasing entropy for this radiation. The black hole entropy, on the other hand, is decreasing. But if this process were to be unitary, we should end up with a pure state, and hence the entropy curve should actually go down. And the time at which this transition occurs is known as the page time. So this was work by Don Page. So as I said, this puzzle has a formal resolution in holography, but it has been an open problem to compute this page curve from a semi-classical point of view. And in 2019, the first group successfully reproduced this phase curve using semi-classical methods. Most of that work involves what's now known as the island formula or quantum extremal surfaces and a switch in the minimal quantum extremal surface. That's not the language that I will use today, but some of the features from these papers will be important. So let me highlight them. Most of the work, the recent work, took place in 2 dimensions, in 2-dimensional JT gravity and ADS. It's a type of dilaton gravity, mostly because it makes the computations very tractable. Typically, this gravitating region will be coupled to a bath. This is often flat space region or non-gravitating region, where there's a coupling to a CFT, and we know how to do 2D CFT computations very well. So from that point of view, it's also a good idea to start in 2 dimensions. Many of the recent papers, they also use a trick that's known as a doubly holographic model, where you start in a d-dimensional spacetime. For simplicity, let's look again at d equals 2. So you have some gravitating region coupled to typically conformal matter. The entire system is dual to a quantum mechanical description, and you can discuss what happens there. But since the matter that you're looking at, the radiation, is itself a CFT, you can choose it to be a holographic CFT that has an ADS dual. And then this combined system is dual to an ADS-free spacetime, typically with some sort of end of the world brane on which this JT gravity is defined. And this is useful because then some computations that in the 2D system are generalized entropy computations that need, for example, this island formula, then reduced to just a simple geometric computation in the higher dimensional spacetime. And indeed, that can be a very useful trick. And with Eric Verlinde, we also developed a model that actually started from 3-dimensional spacetime, BTZ, and then did a partial dimensional reduction down to 2 dimensions to study black hole evaporation here, but using geometric computations in the 3-dimensional system. And because the de Sitter model that I will introduce is along the similar lines, I will very briefly review this construction in BTZ. So again, let me highlight that the most important, I think, tool that we will use is to say that these generalized entropy computations in 2 dimensions are now geometrized in the 3D system. Okay, so in ADS, this is a rough sketch of what we did. I don't want to go into most of the details because they will appear again in the model that I will discuss for de Sitter. So what we did here is we started from a BTZ geometry in 3 dimensions, ADS. And then we did a dimensional reduction down to 2 dimensions, but we did this only for part of the angular direction. So we're integrating out phi, but only up to some value 2 pi alpha, where alpha takes values between 0 and 1. And this gives an ADS2 black hole in JT gravity. And the remainder, the part that we haven't integrated out, we take to be just the original BTC geometry, but then we're interested in its dual CFT that lives here on the boundary, and it couples here to the JT gravity living in this reduced spacetime. And a feature that we'll also see in the DS model is that the dilaton in this JT dilaton gravity gets identified with this parameter alpha and the metric component in the phi direction. And if we then study the boundary dynamics here, what we'll see is that we find an equation of motion for the boundary dilaton that picks up a time dependence, which gets translated to a time dependence in this alpha parameter. And thereby, this partitioning, this dividing line picks up dynamical evolution, and it can evolve. And as I said, then we want to do our computations for the entropy in 3 dimensions. And where we're going to say that the radiation sits in this dual CFT, and it's basically boils down to computing the entropy of an interval in the CFT, basically this interval of the radiation entropy, which then is just a simple geodesic length in the BTZ geometry, where we should take this distance to 0, but I'm just leaving it finite for clarity. And this dynamical alpha parameter then determines whether we are before or after the page time, so the halfway point of evaporation. And we see that once we hit the page time, this minimal surface, it switches. There's a new minimal surface that goes on the other side here. And doing our entropy calculations, we find that the entropy is just a simple function of the angular separation, and this reproduces exactly a page graph. Okay.
Sorry, can I ask? This is equivalent to the usual procedure where, it is equivalent to the usual procedure where you just take JT gravity and couple it to a bath that's outside, that surrounds the black hole. So I'm just still unfamiliar with this language that you're using when you're introducing this defect. Could you just explain the relationship to the original model of Almeri, Maldacena, and Hartmann, and so on?
But the main difference, I think, is, as you're saying there, the CFT is located in an external region outside of the black hole, outside of the ADS spacetime. And here we want to, our main aim was to include this region from the beginning instead of adding it by hand. So we wish to see the bath region as the CFT that, as just the holographic CFT. So it's within the higher dimensional spacetime, it sits there at the boundary.
What is the Lorentzian picture? Is it possible for you to explain what the Lorentzian picture would be? I mean, this is a Euclidean diagram.
This is supposed to be a time slice. Sorry, so.
Oh, I see. This is a time slice.
Yeah, I should have mentioned. Thank you. Yeah, this is just a time slice.
I see. So like some conical part of the ADS space is cut off, and you switched off gravity in that part. And then this is I see. Okay. Right. Okay. Thank you. Yeah.
Thanks for clarifying that. Okay, let me make the transition to the sitter space. That's what we're interested in now. And let me just first highlight a few differences and similarities between black holes in ADS and empty de Sitter space. So this is the Pairwise diagram of Schwarzschild ADS. We know it very well. There's the singularities, the horizons, and we have the left and right asymptotic regions. Has a temperature, has a Bekenstein-Hawking entropy, and it has a first law, which dictates that if you consider a black hole of a higher mass, its area will grow, and thus its entropy grows. Now, the Pairwise diagram of empty de Sitter space is very much alike the Schwarzschild ADS Pairwise diagram in the sense that it's also a square. There is horizons here, but the singularities are replaced by future and past infinity, and the left and right asymptotic regions are, in this case, poles, the north and south pole. So here, time slices are spheres. And an observer sitting here inside what's known as the static patch is surrounded by this cosmological horizon. The horizon also has a temperature and a corresponding entropy, but the first law is a little bit different. So one way that I sometimes think of this as sort of an entropy of ignorance, in the sense that if you have a black hole horizon and you throw stuff in, it's supposed to grow because now there's more stuff inside the black hole that you don't know what it is. But within de Sitter, if you're holding mass at the pole, the horizon comes closer. So Schwarzschild de Sitter has a horizon radius that's less than empty de Sitter. And in a similar way, you could interpret this as saying that once you're holding stuff inside your horizon, you actually know more about what's inside the horizon, and thus your entropy of ignorance is less. So that's one way you could think about this entropy. But as I said, if you want to construct a microscopic description or understand the degrees of freedom that relate to this entropy, it's important to study this. this horizon. And the way that we're going to do that is try to formulate an information problem in de Sitter space. And I guess if you just would formulate an analogous problem as for black holes, you would ask, does the cosmological horizon evaporate in a unitary fashion? Or you could say, is it possible to retrieve what was lost behind the cosmological horizon? There's been some work on this information problem in de Sitter space. This is not, I'm just highlighting a few. And there are a few subtleties that you should take into account if you want to think about this problem in de Sitter. And one is that you can define different types of observers in de Sitter space. I already mentioned this static observer that sits here, who is surrounded by this cosmological horizon. But there's also another interesting observer that you could think about, which is the observer that they sit at future infinity and they have access to the history of the universe. And maybe a more clean way to picture this is, I guess, by adding what is sometimes called the sensor taker's hat. You're defining what is sometimes referred to as the meta observer. And it's just a guy that is sitting here and he has access to everything that came in at the future horizon, at the future infinity. Now, related to defining these two types of observers is a different problem, which is that in de Sitter space, you have to define a vacuum, and maybe the most familiar vacuum is the Bunch-Davies state or the Hartle-Hawking state, where the two static patches are maximally entangled. But in that state, the net flux inside the static patch is actually zero. So it's thermal equilibrium, and the same holds at future infinity. So that's maybe not the most natural state to think about if you want to talk about evaporating horizons. So instead, you'll have to define a different state known as the Unitary state. That's also what we'll do. And then finally, the observer at future infinity is maybe in some sense more like the asymptotic observer in ADS, because he sits at infinity and is decoupled from the rest of the spacetime. But the static patch observer, which is possibly maybe the more natural observer to think about if you want to formulate an information problem, sits inside the spacetime. And thus, if he collects radiation, you need to take into account backreaction. So those are a few important points. And the way we will set up the problem is in a very similar way as I introduced this BTZ, geometry, partial reduction. But now we will start with 3D de Sitter space, reducing it to, on the one hand, the gravitating region, the DS2 in JT gravity, and a thermal bath. Sorry, was there a question? Then we will define this Unitary state, this non-equilibrium state. And we'll take care of backreaction via the dilaton, because in these 2D dilaton gravities, all of the backreaction sits in the dilaton. And then we will use our higher dimensional system to compute the radiation entropy collected by observers at future infinity and inside the static patch. Okay, so let me get to some of the details of our setup. So here, this is maybe my most cluttered slide. I'm introducing the dimensional reduction. So let me first say a few things about this action. This is the JT DS2 gravity. So really the only thing that you should care about is that here we have the dilaton, and varying with respect to the dilaton, it defines the metric to be DS2. There's also a boundary term here, which consists of the boundary value of the dilaton and the extrinsic curvature. This is quite important in JT gravity, as we will see later. Now, the way that we want to end up at this action is starting from 3D Einstein-Hilbert. So we just have our usual Einstein-Hilbert action plus boundary terms. And we're again going to do a reduction, but only along the angular direction, but only up to some parameter alpha, again between 0 and 1. This is our ansatz. And what you'll find is that doing this reduction, you end up with basically the JT action if you identify the dilaton here with this angular component of the metric and the parameter alpha that I introduced. So alpha controls dimensional reduction here, and for alpha equals 1, we've done a full dimensional reduction, and we're left with only JT gravity in the sitter. And for alpha equals 0, we didn't do anything. So here, just to see what this does with the geometry, is the time slice of the sitter. As I said, it's a sphere. And this is the direction var phi. We've done the reduction over this part of the geometry. So here we have reduced to just a two-dimensional system. This is the DS2. And the remainder is still our DS3, which we're going to interpret as a bath. And as I said, the goal is now to make this alpha parameter to make it dynamical. So that's what I'm going to do next.
Sorry, Evita. So is this only for the static patch, or is it for any patch?
No, this is global. Yeah.
Global.
Yeah. So global, in global coordinates, time slices are spheres. We're doing this. Later I will show a picture of the static patch, but we're considering that the same. We're going to consider it as the same reduction for each patch.
Sorry, can I ask a question? So if I'm understanding correctly, you have a time slice, and so out of the sphere, you've cut out some portion and you've turned off gravity on that part. But this part where you cut out is not an asymptotic part, right? It's just some part in the middle. So I mean, how do we know that it's consistent to just turn off gravity in the middle of space like this? So why is that a consistent thing to do?
I'm not sure if we're turning off gravity. We're saying that here we've reduced over this part of the geometry. We've done a dimensional reduction, and there we're left with 2D gravity.
Oh, sorry. In the earlier setup, at least you would need to turn off gravity, right? I mean, all of these calculations work when you turn off gravity at some point, right? Then maybe I didn't understand your earlier setup as well. No,
we are considering, but maybe what's important is that the page curves that we're interested, the entropy calculation that we're interested in, they're 2D computations. So we're not going to think of evaporating three-dimensional de Sitter space, but two-dimensional de Sitter space.
Yeah, no, I understand. But even in two-dimensional space, all the calculations always involve a non-gravitational path, right? Because otherwise, there's no page curve, there's no factorization of the Hilbert space. So now I'm confused. If you don't turn off gravity, I mean, I could have asked it in the earlier setup. I didn't understand that, but maybe here.
But we don't want to. The bath we want to identify with this part of the space-time.
Right.
Sorry, maybe I'm not understanding correctly. Sorry.
The proposal is just that you take two parts of the space-time and you call one the bath and you call the other the system, but you don't turn off gravity anywhere. Is that the proposal? So there's nothing actually happening. There's a tutorial bath. You just need to divide.
Sure. I see what you mean. When we're going to do the computations, we will. So, of course, you can only do these things in regions where gravity is turned off. But we're going to do that at the level of. So we will see that we're going to collect radiation at future infinity, and there gravity does decouple. So this is a non-gravitating region.
I see. So you look at this. I should think of it living at future infinity as being arbitrarily large, and then you're comparing like some part of the. Is that the right way to think of it?
Exactly. I think yeah, that sounds correct.
Okay, thank you.
And then, but I'll get to this later. We're going to do the similar. We're going to identify another decoupled region that sits close to the cosmological horizon for the static patch, and there we're also going to do the computation.
Okay, thank you.
I hope. Sorry, I hope that was clear now.
Well, I'm sorry to belabor this point, but I just want to make sure that I'm getting it just connected to the previous question. So really, you're not turning off gravity anywhere. This thing that you're doing, this dimensional reduction, is just basically just introducing some other parameters, but you're still looking at the full three-dimensional dynamical gravity, right?
Here, so at the level of this reduction, we're doing this just in the full gravitational picture. We're basically just making a partitioning between like one part of the spacetime and the other part of the spacetime. But then when we're going to look at radiation or radiation entropies, we're going to identify two regions that are weakly coupled or that are decoupled from gravity. So where those regions are non-gravitating.
All right. And the second thing earlier you said too, but it was not clear that alpha was dynamical somehow.
Not yet. Yeah, at this stage it's not. Now I'm going to make it dynamical. Yeah.
Okay. All right. Okay. Thanks.
Yeah, so let's get to that actually. So in 2 dimensions, in principle, there's no dynamics. So the way to introduce dynamics in this JT gravity story is to look at a dynamical boundary trajectory. So in de Sitter, the boundary is future infinity. And one introduces this parameter u to make this boundary trajectory dynamical, and then you're going to look at different boundary geometries. And to make this consistent, you have to set boundary conditions on the boundary metric and on the boundary value of the dilaton. And in that case, the extrinsic curvature, so just the boundary term in the action, it reduces to this Schwarzschild action, just like in ADS2 JT gravity. Excuse me. So u here, this parameter is space-like, but as it's going to define for us the dynamical evolution, I will sometimes refer to it as a time. This is abuse of terminology, one could say, but because we see it as a dynamical parameter, we think of it as a time, and later we will also see that this makes sense with respect to the static patch. So what we want is to find this boundary dilaton, which is related to this angular parameter alpha. We want to find the u dependence of this boundary dilaton. And then what that would imply, as I was saying before, that would imply that this dividing line between the gravity and the thermal bath is now dynamical. It's going to move for us. And one way that you can think of this is that the de Sitter entropy in this dimensionally reduced spacetime, which is given by just this simple formula, it's going to decrease as alpha decreases from 1 to 0. So only ds2 to ds2, where the ds2 part is decreasing in size. Right, so this entropy should decrease.
So alpha going to 0 means in terms of u that basically nothing is cut off. Is that right?
Yeah, exactly. Alpha equals 0. It means that there's no ds2 part. So we only have our bath region.
But from the point of view of the u variable, what is that?
Well, I'm going to, on the next slide, you will see how alpha depends on u. And u is just some parameter that goes from 0 to a finite value, just to define this evolution at a future infinity. Did I answer the question? Maybe not.
Well, I think I should just wait and.
Okay, let me know if it's.
Yeah.
Let me know if it's still unclear after the next slide.
All right, thanks.
Okay, so how are we going to achieve this dynamical boundary dilaton? We need to add matter to model our radiation. And then the equation of motion following from the matter term in the action and the Schwarzschild action will give an equation of motion for this boundary dilaton phi r. It's just a differential equation for the energy flux at future infinity. And as I said before, we wish to define a state in which there is a positive incoming flux in the static patch. That's in these static patch coordinates, it means that there's no radiation leaving the future horizon. And translating this to the coordinates that are valid in the future patch, we'll see that that's only right movers. Now, in terms of this u coordinate that I've defined at future infinity, it means that for the stress tensor at future infinity, we find these two components. This just follows from the transformation law of the stress tensor. And then solving for this equation, we find this following behavior for phi r. It's a linear function of u. And so what we've done is we've set 2D evaporating conditions inside this spacetime, took them to the boundary, and see what they mean for this u evolution. And one way to think of this is that at square plus at future infinity, we've sort of set transparent boundary conditions for the flux along this phi direction. And just from this formula, you can define a page time to be the halfway point of evaporation. So this parameter u at the page time is given by this combination of parameters. Okay, so far I've talked about what happens at future infinity, but as I said, we're also interested in collecting radiation inside the static patch. So before I'm going to discuss about these entropy computations that we're going to do in the 3D spacetime, let me show you where we are going to collect the radiation inside the static patch. So maybe to highlight again in relation to the questions that were asked before. So this region, it automatically decouples from gravity because it's future infinity, it's a weakly coupled region. And now we want to identify a similar region within the static patch. Okay, so as I said, in 2D gravity, the metric is fixed to BDS2 and all of the backreaction is encoded in the dilaton, the bulk dilaton node. So in the previous slide, I was discussing the renormalized boundary dilaton at future infinity. Now I'm looking at the dilaton in the bulk. And morally, a similar story holds. So there is just some differential equation for the bulk dilaton in terms of the stress tensor in the bulk. And one can solve for this equation to find the corrected bulk dilaton solution. And if we study this solution, then what we see is that at the cosmological horizon, the bulk dilaton diverges. And this is interpreted as a decoupling from gravity, because in the action, the dilaton sort of appears as the inverse of the gravitational coupling. So a divergent dilaton means a weakly gravitating region, excuse me. So as at Scribe Plus, also we find that the cosmological horizon is a good location to collect radiation. And then starting from this bulk dilaton solution, we can again define a renormalized dilaton as we did for future infinity, but now we can define it at the cosmological horizon. The renormalization procedure is a little bit different, but also similar in nature. And then we find the following behavior, which note is exactly the same as we found earlier for our phi r of u, but now in terms of t. So this time it is a genuine time dependence and not this parameter u. And let me just quickly relate this to something that maybe we can talk about later also, which is that this seems to indicate that the quantum mechanical degrees of freedom for the static patch, that they live at this stretched horizon picture. That's something that has been advocated recently by Lenny Susskind in this series of papers. Yeah, maybe we can talk about that later. Is that clear? So now what I want to do is to consider an observer at future infinity who is collecting radiation there in his non-gravitating region. And then I will discuss this static patch observer who is collecting radiation here.
Sorry, Evita, just to clarify, so in the static patch,
yeah,
where is the Schwarz?
I'm sorry, I have a kind of spiritual doubt. I'm really confused.
Excuse me? Yeah, so I was just asking, in the static patch, like, where is the Schwarzian boundary? Is there a Schwarzian boundary there?
No, so the Schwarzian is defined here.
Yeah, so that's why I'm confused. How can you discuss the static patch in JT gravity?
Well, you can, so what we're doing is JT gravity is defined within the bulk.
Yeah.
And then what we're doing is we're looking at this dilaton solution in the bulk. And we see that also at the cosmological horizon, it shows this divergent behavior, which we then interpret as another weakly coupled region, where we can also identify renormalized dilaton. So it's not via the Schwarzian, but we're seeing this sort of as maybe what I will also say later, like a time-like realization of this future infinity behavior.
Okay, I see. Okay. Yeah. Thank you.
So this we didn't get via the Schwarzian equation of motion. We just got it from the bulk solution, taking that to this location. Okay, so let's start with future.
Can I ask you a question?
Of course.
So, like, this statement about the dialecton blowing up was while approaching the horizons from the sky plus, right?
Sorry, I lost the sound for a bit.
Am I audible? Sorry.
Yeah.
So the statement about the dialecton diverging while approaching the horizon from the sky plus, is it?
Sorry, I lost.
You start from the sky plus for this dialecton, and as you approach the as this future horizons, your dialecton diverges.
Correct.
And,
yeah.
And then we say beyond that, hence you to think of the gravity as weakly coupled beyond that point. Is that the statement?
You're asking what happens behind this surface?
No, the future horizons, both the future horizons, because I thought dialecton had a well-defined boundary at its sky plus, and then the dialecton diverges at the future horizon, right?
Yeah, indeed.
As in the past bound, in the bottom wedge of the forward cone, right? Hence.
You're asking about this surface?
Yeah, isn't the dialectons diverging from there onwards?
Right. So yeah, so the dialecton diverges at this horizon, but in any case, you have to look at different patches. So for the future infinity computation, we're only interested in this patch.
Right. So
and for the static computation, only in this patch. So that's okay.
I see. So I was wondering, why did you say the second asymptotic region kind of lies out in the outside stretch horizon rather than in the past of in the future horizon, while like as when seen from the sky plus? Because
I mean, as seen from, if I understand correctly your question, I mean, if one would be interested in defining a static patch holography, so like a quantum microscopic description of the static patch, we're saying that this seems to indicate that the degrees of freedom that they live here. But that's not relevant for the observer at future infinity.
Okay, thanks.
Did I answer your question? I'm not sure.
Yeah, I was thinking that there's. I was naively interpreting the state. I was naively thinking you should talk. The statement is as a degree of freedom lying close to the future horizon, as in. I mean, the future in the horizon boundary of the forward cone, like in the upper wedge. But that's not the statement you're saying.
No.
Okay, thanks.
Yeah, thanks. Right, so we were going to compute this entropy collected by an observer at future infinity. So here I've drawn the renormalized sphere at future infinity in 3 dimensions, so it's a circle. This is the part that we've reduced over. So there are only these 2 points left, which is future infinity for the 2-dimensional perspective. So it's the S0. So in the Pairwise diagram, that's this surface. And remember, we've set this state such that there's only incoming radiation in this direction. And now the way that we're setting up this entropy computation is we're saying from the higher dimensional point of view, we think of this radiation as moving along this direction phi, remember the dynamical direction. And then the entropy computation that we have to do to compute the entropy of this radiation is an interval of this conformal matter in this region. So what we're going to do is we're going to say at sky plus, the metric reduces. So at this tau time coordinate going to infinity, the metric reduces to this 2-dimensional metric. We're going to map it as well equivalent to flat space. And then we can use our flat space knowledge about CFTs in 2 dimensions to compute this interval entropy. And the interval is where this one space-like coordinate is equal, but the only interval that we care about is this delta phi. And in delta phi immediately enters our alpha that we're then going to imbue with this U dependence. So going through this machinery for this metric, what you find is the radiation entropy in this region delta phi to be given by a very simple dependence on alpha. And plotting this for our alpha view that I've shown on the previous slide. So basically just 1 minus constant view. We find this curve for the entropy. And the way that we like to interpret this is that naturally an observer at future infinity would see a unitary evaporation of the cosmological horizon. So we go from a pure state to a pure state. So I want to stress again that this 3D system is auxiliary. So the evaporation is two-dimensional, and we've just geometrized this computation in this 3D geometry. Maybe what I will also say, but I will get back to this later, is that really what we will find is that backreaction becomes important exactly at the page time. So it's unclear if we can trust this computation after the page time, but we still think that it has something to say about, in principle, this observer would see unitary evaporation. This is different in the static patch. So there, the way we set up the computation in 3D is in 2D. Remember, we're going to collect this radiation close to the cosmological horizon. So this is not a Pairwise diagram. This is a drawing of the static patch. It's like a cylinder. Excuse me. And then in 3 dimensions here, I've embedded the 2D static patch inside the 3D static patch. Here we see the reduction. So this is our 2D system. This is the 3D static patch. And again, this radiation is collected close to the cosmological horizon. If we look at this 2D subsystem, it's flat and it's thermal. So we can use our thermal CFT formula. And if we do so for this angular separation delta phi, in terms of alpha, we find a very similar behavior, but crucially different. Instead of a sine, we find a sinh. And this is in principle an ever increasing formula. And thus, if to find a unitary curve, what we should do is something similar as I mentioned for our BTZ computation, where there should be a jump in a minimal surface. So in the 2D system, this would mean that you would have to use the island formula to find this unitary curve, contrary to the observer at future infinity who naturally observes a pure state. So I'm saying that after the page time, instead of looking at delta phi, you should look at the complementary interval, and then this curve would go down. But again, I've drawn these dashed lines to indicate that we think that you should not trust the computation after the page time anyway. So let me explain why.
The initial state for the static patch is that not a thermal state?
Yeah, but yeah, indeed.
Then why would entropy be 0 at initial?
Well, but remember that we're looking now at the entropy of the collected radiation. So we're measuring that in this path region, which initially there it has 0 entropy. So indeed, the entropy of the static patch itself, it should go down in this way.
Okay.
Is that okay?
Yeah. Yeah, thank you.
So what happens at the page time? Why are we worried? So the problem is that a trap region is going to form. And let me explain what I mean. Trap region forms if the null derivatives of the bulk dilaton are negative. And to see this, maybe let's recall our flat space intuition. So if you have some surface here, you can define an outgoing and an ingoing null ray, and then look if they, and then you can see if they diverge or converge. And from flat space, your intuition would be that ingoing null rays converge and outgoing null rays diverge. So the surface would grow. But in curved spacetimes, this can be different. So for example, inside a black hole, collapsing matter here, within this apparent horizon, you'll find that both expansion scalars, both these expansion scalars classifying if these things diverge or converge, both will be negative. And in JT gravity, these expansion scalars are linked to derivatives of the dilaton. Why? Well, this expansion is really like just a change in volume. And remember that from the higher dimensional point of view, this dilaton is like the size of the transverse sphere. So also here, this is related to a change in volume. So you will have to look at the null derivatives of the bulk dilaton, and where they are negative, a trap region will form. And we've computed this for a corrected bulk dilaton, and we find that this happens exactly at the page time. So this is the boundaries of this trap region. And the way you should think of this is that radiation that is coming from this fast horizon, once it enters this region, it's trapped. So it can never reach the observer sitting here. And this also has an effect on our meta observer, because so here I've drawn this sensor taker's hat. So someone collecting radiation here about the history of the universe. What we will see is that only radiation that arrived at future infinity before this value for u can be measured. Actually, the situation appears to be a little bit more dramatic. This was outlined in this paper by Alsma and Siebesma, where they also considered quantum singularity theorem for a similar setup as ours. And they find that within this region, actually, a quantum singularity forms, and this static observer is bound to hit, his world line will hit that singularity. And we think a similar story would also apply to our case. So as I said, we think we should only trust these entropy curves up to either this T trap, this page time, or this U trap. Okay, so what have we seen? We started from a three-dimensional de Sitter space, reducing it to a two-dimensional de Sitter space plus a bath. We defined this Unruh state to set a non-equilibrium state that evaporates. And then I looked at the boundary dilaton at future infinity, linking it to this alpha of u, this dividing line between these two systems. And this Unruh state sets this phi r, this renormalized dilaton, to be dynamical, and thus also this dividing line is dynamical. Then we looked at the backreacted bulk dilaton to signal another decoupling region, but this time close to the cosmological horizon. So both future infinity and the cosmological horizon are non-gravitating regions in this setup. And this allowed us to compute both the fine-grained entropy at future infinity and inside the static patch. And we saw here that this observer would naturally observe a page curve, whereas here you would have to make use of the island formula to define a new minimal surface. But then what I argued is that backreaction effects fatally obstruct both observers from witnessing this curve, and you should really end it at the page time, or at this page time in terms of u. Maybe a few points that I think are interesting to discuss is, so notice that at future infinity, I'm claiming that we don't need islands to see unitary evaporation. And I think this is in line also with work on islands in de Sitter by these authors, where they looked at islands in Schwarzschild de Sitter in 2 dimensions. And then they were also considering what would happen if you look at pure de Sitter in higher dimensions or in 2 dimensions. And they're formulating sort of a no-go conjecture that you would find no islands for an entangling region at future infinity. And this is actually, I think, is consistent with what we're finding, because indeed we don't find this change in minimal surface at future infinity, contrary to the static patch. Then one other point that I think is interesting to look at also in the future is that we noticed that there's this weakly coupling region at the cosmological horizon, where this could be a natural point to locate the quantum mechanical degrees of freedom in this language of a stretch horizon. And would be interesting to make the connection to work by Lenny Susskind and others to define this static patch holography. But I think what we're seeing goes maybe even a bit further, which is that this cosmological horizon, where the dynamics is in terms of static patch time t, is linked to the dynamics at future infinity in terms of this parameter u. So it seems like what we're seeing there is a time-like realization of the dynamics at future infinity. And it will be interesting to see how far this connection can be pushed. Thanks.
Okay, thank you very much, Evita, for the great talk. So are there any questions?
I have a quick question. The craft surface that you found, so are you saying that if you take three-dimensional de Sitter and you put just the unruh boundary conditions, then in the bulk or close to the static observer, you will have craft surface at some time? Is that what's been shown here?
No, sorry, the claim is only for 2D, and indeed it's not clear if this will hold also in higher dimensions, actually, to me. Because this relied crucially on this bulk dilaton divergence, and I'm not sure that this can be extrapolated to higher dimensions in that sense.
Well, so if I just take de Sitter 3 and I just impose unruh boundary condition, then you're sure that this thing does not happen in that case, or you're saying we don't know what happened?
I'm saying we don't know.
Okay, so one could in principle check whether the quantum singularity theorem would just...
Indeed, and I think that would be interesting to check. Yeah.
Okay, all right, thank you.
I had a question, ma'am. Excuse me, am I audible?
Yeah, I can hear you.
If there's a charged black hole, then how will the boundary conditions at the cosmological horizon change, and how will the time dependence of the parameter change of the alpha parameter? If you have a charged black hole.
If there's a black hole, so we didn't consider any black hole, but you're asking what happens if we consider Schwarzschild de Sitter?
Yes.
Or I guess a charged black hole in de Sitter?
Yes.
Well, in 2 dimensions, then you would have to consider a doubled Pairwise diagram. So, so note that we were looking at this Pairwise diagram for DS2, but another way to draw the DS2 Pairwise diagram is a doubled version, where you also have black hole horizons, and these sites are identified. So this would be a model for higher dimensional black holes, but we were looking at a model for higher dimensional empty de Sitter. This has been studied also in this paper that I mentioned earlier, but also by these authors. So there's the extended Pairwise diagram in 2 dimensions, and they are finding they are looking at, okay. So these authors are looking at islands at future infinity, so for radiation collected there, and these authors are also interested in the static patch, and they also define the Unruh state, and both find a page curve there. So, but that relies on the island formula. So we're not sure how to extend our setup to the case where there's also a black hole.
Okay, thank you, ma'am. Yes.
Yeah, Evita, I also had a question. So just coming back to the question I asked. So in the static patch setup, you had you said the dilaton was diverging at the horizon, right?
Yeah.
But in JT gravity, this is how you define the cutoff boundary, right? It's the place where the dilaton diverges. So it seems that there should be maybe a way, because there should be maybe a way to do like JT gravity in the static patch.
Yeah. I think it smells like that. Yeah, but yeah. So you're saying you should find like a Schwarzschild description also there. Schwarzschild.
Yes, because so in the vacuum it doesn't work because the electron won't diverge there. But basically, you found that if you add matter, it does diverge. So, yeah, this was just a comment. Yeah.
Yeah. No, indeed. Yeah, and I think I thought that was a bit surprising and interesting, and yeah, would be interesting to look at that further. Note that they also find like another weakly coupled region in their setup. So yeah, it should be possible to make the connection more precise also to their work.
And do you have anything more to say about this static patch holography that you mentioned?
At this stage, no, not really. I do think it's important to look at to formulate a static patch holography, and there have been different proposals. I guess also there's work by Diego Hofmann and Dionisio Zaninos about the quantum mechanical realization of the world line. So that's a candidate, I think, for static patch holography. But from this point of view, I think it seems like you could find a formulation for these quantum mechanical degrees of freedom to live at this cosmological horizon. But I'm still digesting also a bit the papers by Susskind, and I think that should be an interesting region to look for this holography. But yeah, I don't have anything more concrete to say at this point.
Okay, thank you.
So maybe this is a restatement of the previous question, but the fact that phi goes to infinity at these horizons is a statement that gravity becomes weakly coupled. But you're saying that this is not evident in the original DS3, but only appears after the dimensional reduction. Is that right? Or is there some intuitive way to understand why gravity decouples at the horizon?
Indeed, I'm saying that this happens in 2 dimensions. In 3 dimensions, we're really just using this as an auxiliary system to do the computation. So it's not, to me, it's not clear from the 3-dimensional point of view why that would happen at the horizon. No.
It's just something that happens when you do the dimensional reduction. Is there an intuitive understanding of why gravity decouples at this point? I mean, at the horizon.
Let me see.
I mean, it seems a bit strange to me that if you have a system with dynamical gravity and then you do a dimensional reduction and then you find that at some point you have a place where gravity switches off, and that's what worries me. How does that happen as a result just of dimensional reduction?
I'm not sure it's a direct result of the dimensional reduction. I think it happens in this JT gravity model that in principle you could have started from scratch.
So let me understand once again. You start with a DS3 and then you reduce it to DS2, so you get a theory of JT gravity on DS2, right? Is that correct? Mm-hmm. So the original DS3 also there was a cosmological horizon, but it's not true that gravity is weakly coupled at that horizon.
No, I don't think so. No.
Right. So somehow by doing a dimensional reduction, you end up with a system where gravity is now weakly coupled where it was not weakly coupled earlier. That's confusing me.
Well, but would you say, I'm not sure that the horizons, they're not the same, right? Would you say that the 2D horizon overlaps with the 3D horizon?
Oh, sorry, don't they? Maybe I didn't understand the geometry. I thought the 2D horizon, you do a dimensional reduction on one of the sphere directions, right? So in terms of isn't the 2D horizon a cross section of the 3D horizon? I mean, there's an extra direction in 3D.
Yeah, that's true. Yeah.
But then you seem to be saying that in the original 3D horizon, there was no point at which gravity was weakly coupled, but after the dimensional reduction, it is becoming weakly coupled, and that's what I'm finding confusing. I mean, why should that make gravity switch off at some point?
I see what you're saying. I'm not. Yeah, I don't. I don't find it very intuitive either. It was also, as I said, surprising to us that we found this region, but we do see it in the 2D geometry. I'm not sure. I'm not sure why this would happen from the 3D point of view.
Okay. Okay.
But yeah, it's a good comment, and I will definitely think about it.
Okay, thank you.
I had a question.
Please, yeah.
So in the beginning of the talk, you had mentioned about microstates. Could you please elaborate a little bit?
Right. So I think that's mostly related to this last comment I made about these degrees of freedom living here at this, or no, I lost it. No. At this horizon. So I think what I was saying about microstates is that if we were to build a microscopic model of our universe or of our static patch, that would be a natural place to start, since that's what we observe as people living in this phase of expansion. Then you would have to locate these quantum mechanical degrees of freedom. And what we're seeing is that a good location, a good candidate location for this could be this cosmological stretched horizon. But we haven't, I mean, this is something that we should explore further to see if you can indeed locate these microstates there.
And I did notice that you had the Schwarzschild action in one of your slides, and clearly we know that the Schwarzschild action describes the infrared physics of the SYK model. So
correct. Yeah, that's true.
So would you be tempted to say that the microstates are precisely these fermions of the SYK model? I
think this is what, for example, Herman Verlinde, but also Lenny Susskind are I think trying to investigate, which is that the SYK could be dual to de Sitter instead of anti-de Sitter. But I haven't fully digested this statement, but yeah, we are thinking about this.
So I guess the issue would be what is the time of de Sitter as opposed to the time of anti-de Sitter. There is a time in the Hamiltonian of the SYK model. So I guess you'd be worried about what it's conjugate to in de Sitter as opposed to in anti-de Sitter.
Yeah, that's a good point. Yeah, indeed.
Okay. Thank you.
So what's the relation between the three-dimensional Newton's constant and the two-dimensional Newton's constant? Is it not just simply phi times 2g is equal to 3g?
Sorry? The relation between, we are identifying, let me get this correct, to this. Is that what you're asking?
Yeah, that's L. So there is no phi. So in what sense? Now I don't even understand in what sense two-dimensional gravity becomes goes to what do you call it?
Maybe let me go back to this slide.
In what sense two-dimensional gravity decouples
well, okay, I see. No, so what we're saying is that here in this action, a divergent phi can also be interpreted as g going to 0. That's sort of the trade-off that we're making.
That's exactly why I was asking what's the relation, because it seems like the relation you wrote, there does not seem to be any phi there, and from that.
Right. So I think maybe that's related to also the question earlier about what does it mean from the 3D point of view that this region is weakly coupled, but
well, clearly
I'm just saying that
from 3D point of view, there is nothing is weakly coupled. I mean, Newton constant is there, the gravity is there, and everything is there.
Exactly.
It's only from two-dimensional point of view that your magic is happening. So it's
Indeed. That's correct. Yeah.
So from the action, it seems like when phi goes to infinity, G2 should go to, I don't know.
Sorry, I don't think I'm.
I'm sorry, it's my internet connection that's very unstable. So please go ahead. You say what you want to say.
No, I just, yeah, I'm not sure I understand the question.
Well, I guess it's just a previous question. I was just thinking, I thought that somehow phi goes to infinity, then G2 has to go to 0 so that G3 is finite. But phi does not even show up in G3 anywhere. So I don't really know how to see that gravity switches off when phi is infinite.
Maybe one thing that we should be careful with is that, so we don't have, so this action, it still holds here in this region. And it's only here that we have this action. And we're no longer thinking about the 3D geometry there. Maybe, but I'm not sure if that.
Okay, that's fine. But that seems like some kind of a very clever reparameterization, right? So that you can talk about two separate degrees of freedom as phi and two-dimensional G, right? So far,
I think it's mostly just a construction to go ahead.
No, just a comment, maybe if I understood the question. So in 2D, the effective Newton constant is, you can think of it as what multiplies the Ricci scalar is really phi divided by G2.
Yeah,
so
exactly.
phi goes to infinity is similar to G2 into 0.
Exactly. But yeah, indeed, that's the claim. But I think the worry is about 3D. But again, let me stress that we are just using the three-dimensional geometry as a tool to compute these entropies, and we're not interpreting that in any other way at this stage.
okay. Thank you.
Are there more questions for Evita? Okay, maybe I can just ask the last question, just a discussion question, maybe, because you said at some point that you didn't believe that this would hold in higher dimensions. I mean, is this just, do you have a reason to say that, or just an intuition?
I just feel like many of the features that we saw here depended on the behavior of the dilaton, and I'm not entirely sure how to upgrade this to higher dimensions. So yeah, it's something that we're definitely interested in, but yeah, that's my reason for being a bit hesitant to say anything about higher dimensions.
Okay, I see. Thanks. Is there a last question? Okay, if not, let us all thanks Evita again for the very interesting talk. And yeah, thank you very much, Evita.
Thank you for having me.
Yeah, no. Okay, so I'll end the meeting now. Bye.
Thanks, bye-bye.